Okay, uh, just give me a minute. Let me just try something. Yeah, how is it now? Okay. If someone can just pop over to YouTube, just tell me if you can hear me on that too. Hey, Ashir. Right, okay. That's great. So, yeah, we had a little bit left of the lifting the. No, sorry, we're just starting. We had a couple of slides left of the lifting the exponent lemma, and then we'll start with today's topic. Right. So, last class we basically stopped at the case when the case about 2. We looked at all the odd primes, if you remember, and in fact I have a list of Ashir. So today we are basically looking into we had that question where it was super necessary to find the square root of 2 to the fourth or the fifth decimal point, right? So yeah, today we'll be looking at root finding algorithms mainly, but let's just finish this first. After that, yeah, I'll just check. We might do either some probabilistic number theory or uh, move on to something. I'll check and tell you the final plan. Right. So just to finish this off, guys, it over at the YouTube and Facebook streams. This is just the last end of a topic that we were covering. We'll start with a new topic pretty soon in like 5 minutes or so, hopefully. But we had taken, yeah, we had already looked at these two conditions. That is, we looked at all the conditions for odd primes, both for addition and subtraction. And we had looked at the case when 2 does not divide the exponent. And this is true irrespective of whether the prime is 2 or not, right? So, looking at the next case of, you know, when p is equal to 2, we divide it into two sub cases. One where 4 divides a minus b, and then we'll generalize to another sub case where, okay, let me just change the color first of all. Right. One where 4 does not divide a minus b, and then we'll generalize this to the case where 2 divides the exponent. And then we don't need the 4 divides a minus b anymore, right? So let me start a whiteboard. So the first case is when p is equal to 2, 2 does not divide a comma b, sorry, a comma b, and 4 divides a minus b, and we have to find basically v2 of a raised to n minus b raised to n. Uh Right. So honestly, it's actually not extremely trivial, especially keeping more than the formula itself is all of the prerequisites that are needed to ensure that you are using the formula right. Correct. Yeah, I mean the formula should definitely be trivial. It's just that you need to exactly. That's true, but also you always need to ensure that, I mean, either you know or I'm not sure how you'll derive, but you always need to ensure that the conditions follow, because it's extremely easy to apply the result of LTE without verifying the uh, required prerequisite conditions, and then that just negates everything. Yes, exactly. So, yeah, going back, in this case, what we basically have to do then is, um, right. So, for two, obviously, from our previous topic, we already have this case, like already proved the case when 2 does not divide the n, because that's directly the extreme first case that we took, right, where it just equals v of a minus b. Then v2 of a raised to n minus b raised to n is equal to v2 of a minus b. Right. So given this, for the general theorem that we need to prove, I'll just write n as equal to 2 raised to k times l, right? And then directly from this, we get that this is just equal to v2 of a raised to 2 raised to k minus b raised to 2 raised to k, right? Good. So what we basically need to, yeah, Arjun, I have a list of it here, but so basically what you need to remember, I mean, in this case, this should be the only one I use, this and the multiplicative formula. So vp of a into b is equal to vp of a into vp of b, right? So yeah, though do make sure that you go back and either read or watch some material to remember this. So this we can write as v2 of, let's say, a raised to 2 raised to k. This can be written as your a raised to 2 raised to k minus 1 plus b raised to 2 raised to k minus 1 times a raised to 2 raised to k minus 2 plus b raised to 2 raised to k minus 2, and so on, right? 2 raised to k minus 2, and so on up to a plus b and then a minus b. right? Now, one thing that these conditions allow us to assume is that A congruent to B congruent to plus minus 1 mod 4. Any doubts in that? Since 2 does not divide A and B cannot be congruent to 2 or 4 mod 4, and 4 divides A minus B, hence A is congruent to B, congruent to either 1 or 3, it's minus 1. So A congruent to B congruent to plus minus 1 mod 4. Yeah, so just putting this back down here, that means A raised to 2 raised to anything will be congruent to 1 mod 4. So A raised to 2 raised to k is congruent to 1, B raised to 2 raised to k is congruent to 1. So this whole thing is congruent to 2 mod 4. And hence V2 of this number is exactly 1. Similarly, V2 of this is exactly 1 up to V2 of this is exactly 1. Right? So this will just be equal to k minus 1 plus Arjun, I didn't get you. Since n is equal to 2 raised to k into L, we've already taken care of L, because if 2 does not divide n, so first what we did is a raised to, instead of a raised to n, we took the number a raised to 2 raised to k, the whole raised to L, and b raised to 2 raised to k, the whole raised to L. Those over at YouTube, as I mentioned, just give me a couple of minutes. We're just finishing up with this, and then we'll start with a new topic. Right. And then once we have it in this form, we can apply the original one, which just says that if 2 does not divide n, then v2 of a raised to n minus b raised to n is just equal to v2 of a minus b. So v2 of 2 raised to k times L is minus, I mean, a raised to 2 raised to k times L minus b raised to 2 raised to k times L is just the same as v2 of a raised to 2 raised to k minus b raised to 2 raised to k, right? Um, yeah. So finally, uh, just give me a minute. Yeah. So this will just be okay. My net is a bit slow. Just give me a minute. Let me see. Right. So this will just give you k plus v of a minus b. V2 of, which is just v2 of n plus v2 of a minus b. Because all of these, like v2 of all of these evaluates to 1, right? So that gives us the first new formula, which is if 2 does not divide a minus b and 4 divides a minus b, then a raised to n minus b raised to n, v2 of a raised to n minus b raised to n is equal to v2 of a minus b plus v2 of n. And this can be pretty easily expanded to the second case. When 2 divides n, what we'll do is no. So that's the thing with LTE is you have a variety of different cases, each having its own conditions, and you have to check which conditions are satisfied and which result you have to use. Generally, the result is of the form VP of A plus minus B plus VP of N, except for this last case that we consider, where it's a little bit more complicated. But again, you'll have to keep track of each precondition and decide which precondition actually works for you, and verify that all of the requirements for that condition actually are correct before using LTE. Right, so the final case is when 2 does not divide A and B, but 2 divides N. Then what we basically do is, if 2 does not divide A comma B, then A square congruent to B square congruent to 1 mod 4, right? So what we do is, here within case 1, instead of A and B, we'll use uh, A square and B square. Right. So what we'll get then is v2 of a square minus b square plus v2 of n minus 1, because we sorry, plus v2 of n by 2, which is v2 of n minus 1. uh yeah, exactly. So none of these steps per se, would I say, is difficult. It's not like you are like the derivations we went through while uh, proving quadratic reciprocity. Each step, each derivation per se is easy. It's just, you know, tedious. It's long. So yeah, using the previous formula for a square and b square, we get that b2 of a square raised to n by 2. Yeah, all of these, at least in their current definitions, are all discrete, so you cannot really take derivatives. And then this gives us b2 of n by 2 plus b2 of a square minus b square, because for you to be able to take a derivative of something, the function needs to be continuous. And as we have defined it here, at least, the functions are valid only for integers, so by definition they're not continuous, right? You can create a superset of try to create a superset of this which achieves the exact numbers at the integers, but uh, So which polynomial are you talking about? Plus v2 of a minus b plus v2 of a plus b. Yeah, f of x is definitely continuous, but uh, this, the v2 function or vp function, is defined only for integers, right? Because what's the, well, in fact, I think it is possible to extend this to rationals also, but what, for example, is the v3 of pi or v2 of pi? Exactly. So at best, you can extend this to the rational numbers, but yeah. So you will have to find a sane way to lift the definition of VP to reals before being able to use uh, differentials and integrals. It's definitely possible to use it within the realm of number theory, but first you'll have to convert the whatever you're looking at into continuous functions. So there have been cases where, discrete functions have been generalized into continuous functions, the most famous of which I think is the factorial functions. There are a few really good extensions of the, right. Yes, I think we can extend this to Gaussian integers, by the way. uh, Yes, factorial is extremely famous because its continuous form is another extremely famous function, gamma of n minus 1. Yeah. So similarly, if you're able to figure out a continuous extension of VP, then it might be exactly, that's true. Then you might be able to use differentials and integrals. Yeah, again, Gaussian integers are definitely discrete, so extension there cannot really help you in uh, differentials, right? So with this, we can move to the main topic of today. If you have any doubts in this, you can ask either right now or whenever you come across them. This is basically a summary chart, but yeah. So let's start with the main topic of today, and that is how to find the roots of, yeah, definitely, Arjun. So how to find the roots of any, okay, how to find the roots of any algorithms. uh, so what I'll be discussing will be, roots of any polynomial, but generally the, what do you say, the trickier your polynomial, the harder it will be to, because most of these are iterative methods, the harder it will be to actually use these methods, right? So as I mentioned, this is a part of uh, generally the branch called numerical analysis, which at least for me I encountered actually in the second year of college only. So I was really surprised that you need a root of a very large decimal place. uh, you need the value of square root of 2 to a very large decimal place. But since you have shown me an example of where it can be used in an IMO, we'll just run through it. Should not, fingers crossed, it should not appear much in within the IMOs, but these are generally easy uh, techniques. So you can just keep these in your mind, and if it ever comes, you can use it. Right. So the first, sorry. So I don't know about save your time, because honestly most of these techniques are used in a computer system, so they generally use a lot of very I'll come to that. They generally use a lot of um, squares, uh, multiplications, divisions, and so on. Yes, it's the intermediate value theorem. So let's first talk about our problem here. Problem is simple. In this case, let's say this is some polynomial, some f of x, and we need to find the value of x at which f of x is 0, right? So to find roots, you'll just take f of x, for example, as x square minus 2, and you'll find the value of x where it touches 0. So the first example of such an algorithm is bisection, which uses, as already mentioned, the intermediate value theorem. So yeah, I hope all of you know the theorem. Does anybody want to just explain it? Right. So the intermediate value theorem, well, the basic result that I'll be using is that in such a case, especially for an odd multiplicity root, you will have, if a and b are two values, uh, if x lies between a and b, then f of a and f of b will have opposite signs. Is that fine? So honest method, at least currently, I haven't added it. I thought that was, somewhat uh, involved, too involved, I'd say. You think you'd need it? Actually, I might just, yeah, I'll just ask around, and if it's required, I might just take the first 15 minutes or so of the, or it might take longer. I might take half a lecture or so on it. But let me just ask around and find out whether it's really relevant to you. So yeah, going back to bisection, it basically uses the fact that, at least for, so one of the drawbacks of bisection actually is that it cannot find roots with even multiplicity, but for roots with odd multiplicity, you know that if a and b are at two sides of x, and there are no, second roots here, so if a and b are fairly close to x, f of a and f of b will have opposite signs. So what I do then is I just take the value a plus b by 2, the mean of it, and I see which sign this has. So if this is positive, then I will replace b with a plus b by 2. If it's negative, I'll replace a, IVT, intermediate value theorem. Intermediate value theorem is a pretty famous theorem. It states that uh, well, actually for a continuous function which moves from A to B, basically you can find all, you can if C lies between A and B, so let's say actually f of A is x. This is a pretty famous theorem. You should be able to find this pretty much anywhere. Is y for any c which lies between x and y. For now, I'm taking x is smaller than y, but it can actually be the opposite. I think so. I think you can use it directly. Then for all c that lies between x and y, there exists at least one value of uh, f of, actually for all z, let's say between x and y, there exists at least one value c such that f of c is equal to z, where z is between x and y. So basically within the let's say if the function evaluates to values between x and y and it's continuous, then for any value between x and y you should be able to find an inverse. Right. So yeah, this is the intermediate value theorem. Mean value theorem uh, is about differentiation. It says that it actually goes something like this, but instead of f of c equal to z, you have f dash c is equal to y minus x upon a minus b, if I'm not wrong. Yeah, you have at least one c such that f dash c is equal to y minus x upon sorry, b minus a, b minus a. Either way, so this is the mean value theorem, this is the intermediate value theorem. So again, applied to roots, what that basically means is that if there is a negatively value, if there's a negative value integer here and a positive value integer here, then there must exist a root in between, right? And we all and we know that uh, this is if this root has an odd multiplicity, then it crosses the x-axis instead of just being tangential to it, because uh, one side has to be negative and the other side has to be positive. So with that, let's see what bisection says. What bisection does is, let me take an example. New whiteboard, and let's say I'm trying to find the square root of 2. So x square minus 2 is equal to 0. Then what I do is I find uh, let's say two values, x equal to 1.414, between with 1 and 2 it will actually take a lot of uh, iterations. So the closer you are to the root, the better. So so if you know, for example, that it is 1.414 something, I would suggest starting just with 1.414 and 1.415 or something, right? So the next number then that we'll be looking at is the mean of this, that is 1.4145. 4145. So plugging this into the equation, 1.4145 square minus 2 will be, this is basically equivalent to a binary search. It is positive and it gives us about 0.0008. Yeah. So what we'll do is then we'll take 1.414 and 1.4145. And the mean of this is 1.41425. So again, this is the reason, yeah, why it is, this method is tedious. It's because you will have to keep multiplying such a big number with itself. Just, you know, multiply with itself 1.41425 and multiply it out, right? So again, that's why I told that many of these algorithms are actually designed for use in computers, because then squaring is pretty straightforward. It's just a single operation on a chip. But yeah, 1.41425, let's see. So in this case, you will have to perform this multiplication as many times as you want to iterate. So as many, as close as you want to the actual root that you want to get, that many more times you have to multiply, and that's the overhead that you face. With 1.41425, that is still, x square minus 2 is still greater than 0. It's about 0.0010. So 0.00010 something 3, right? So we can continue with this. So for example, what we know at this step itself is that square root of 2 is less than 1.412425. And let's actually see whether this is enough to solve the question that you had, right? So the, yeah, but then that will just take an infinitely large amount of time, especially in a question like, I mean, in a place like IMO where you cannot use calculator. So this was the original question that prompted this discussion. So let's see what 1004 into this is. 1004 into 1.41425. Right, that comes out to 1419.907. 0.9, which is less than 1420. So in fact, even in our second step here, after two self multiplications, we found this result, and with this result we can conclusively prove this, right? So yeah, exactly, Saradeep. What I'm trying to do is to find a good square root of 2 which can, be used for steps like proving this. So yeah, any doubts in this method? Right. So, in fact, for square roots, generally, this is what we'll be following, where we'll just do an x plus y by 2 format. And then recalculating, but actually, do we need to recalculate? No. So, the next method might help us with that. Actually, this met this is a this is actually a hit and touch method, fixed point iteration, and generally will not be of much use in the IMO because because for so again it's an iterative method and we do not have a guarantee that it will converge. And for the best chance of convergence, let's say you want to find x cube minus 3x, for example, plus 1, just to make it difficult. Right. What you need to find is to write this equation as x equal to some function of x. There are two ways to do this, if you see. Let me use a white color pen from now on. One way is x is equal to x cube plus 1 upon 3. Right. I'm trying to find the root of this is equal to 0. And the other way is to write x as the cube root of, uh, let's see, 3x minus 1, right? Now, what we're doing then is we are trying to iteratively keep using this formula. And so we'll start with a number, let's say x equal to 1. Then we put that into this formula to find a new x, put that again into this formula to find a new x, and so on. So what we ideally want is that if this is the root and we started out here, we the next one reaches somewhere here, or I mean taking the mod of the value. So let's say this is the point at the same distance, call that y. So we want the next iteration to lie within this realm, right? And then it can get shorter and shorter. But what the simpler method here will do is that by changing the value of x a little bit, the value of x cube will change much in a much larger way. But what we want to do is that we have changed the value of x from its actual value to something else by y. We want the new value of x in a way to be less than mod y distance from the actual root. Does that make sense? Yeah. So such a method which is simpler to perform the calculations on will often diverge. And for this method, the fixed point iteration method, to actually work, we need to take the highest root out. So write this in the form of the highest root and then take roots on both the sides. But then this becomes extremely complicated to solve out, especially on paper, because the cube root itself is extremely difficult to solve. So this can be used pretty efficiently on things like a computer, but for the IMO, this is unfortunately not very useful. Even if you have a calci, for example, that you can always use to find cube roots, this is pretty useful. But when you have no tools whatsoever, this is not a realistic method to follow. I hope that's clear to everyone. So the basic method this rule uses is to write the whole thing as a formula of x. We generate x from the formula itself, and then we uh, repetitively go through this formula and find the value of x at every turn. And it's not really possible to use it in an IMO because it generally uses roots of very high powers, which cannot be uh, solved trivially in your exam setting. So then we come to the next method, right? So the Newton-Raphson method is actually a pretty useful method. It converges quickly too, and what it does is, well, let me show you what it does first. So let's say again these are pretty complicated methods, and their proofs generally include a lot of derivatives in it, which is the reason why I skipped them. Since they are well known, I would expect that these methods can be used just right out of the box. But if you want the proof, I'll link you to, I'll share a link to a PDF with most of the proofs, I think. There's a lot of things actually to prove here. One, that this equation actually makes sense, which is actually a very small thing to prove. The more important proofs for using this as a method is to show that such methods, either fixed point or bisection or even Newton-Raphson, actually converge. That's generally non-trivial, especially because in many of these cases you have specific subcases where convergence is not expected, right? So yeah, let's go back to the Newton-Raphson method. What it does is, basically, let's assume this is continuous and you are here, right? This will ideally be curving upwards. So it finds the derivative at this point and then moves from this original value of x to this new point where the derivative hits the x-axis. And since this is curved either way, upwards or downwards, in this case it is curved upwards, that means that this will always lie before this point. So we'll continue doing it here again, find the new point where the derivative hits the x-axis and move there, and so on. So how we do that is by using this formula. So this value here, this is f of x, and if you remember what the derivative is the tangent of this. So f dash of x is just let's call this t. F dash of x can be written as f of x upon t. So t is f of x upon f dash of x. So we are subtracting t, and hence the new value becomes x minus f of x upon f dash of x. Is that clear? Right. So that's basically our formula. We start with some guess of what f of x is, and then we always use this value of f of x minus f dash of x. Now for square root, this basically becomes equal to, sorry, x minus x square minus a, let's say. So we are looking at the square root of a upon 2x, and this will then solve, if you see, to half of x plus a by x. This uses, instead of using squaring, this will use a lot of divisions. right? And this is actually a well-known algorithm before, the generalization by Newton-Raphson. This, I think, was called the Babylonian algorithm and was well known to find the roots of numbers. So again, taking the example of uh, square root of 2 with the initial value of 1.414. Let's take 1.415 for example. You want the value that square root of 2 is less than. Then this will then go to half of times 1.415 plus 2 over 1.415, which is going to be difficult to calculate. 1.413427, 1.4134, so on. Right, and then you continue this way. Oh, plus 1.415 over 2. This, for example, gives you 1.414213, which is extremely close to the actual number. 41421 789 something, 78 blah blah blah. And this is extremely close to the actual value of square root of 2. I think it's 6 digits, correct. 41421 so the actual value differs by less than sorry 2 upon 10 raised to 1 2 3 4 5 6 7. Yeah, exactly. So the actual value differs less than 2 upon 10 raised to 7. So from 3 digits of accuracy, we have gone directly to 6 digits of accuracy. And the what do you say? What you pay for that is, Arjun, I didn't get what you are unable to understand. Here, what you do is half for any input number that you have, you write it as half times x plus a over x. Or if you want the square root of 2, this becomes half times x plus 2 over x, right? This was a general formula for square root of a. This is the formula for square root of 2. So I took the value of 1.415 to start with, and I just put it, put the value in here, and the very next iteration that I got is this number here, 1.41421 The non-trivial part here is actually dividing 2 by 1.415, which will take a significant amount of a non-trivial amount of time at least. And once you do that, you'll get this number, which is uh, correct up to 6 digits or 6 decimal points of the value of square root of 2. Arjun, is that summary good enough? Yeah. So, and then this again, so I mean, I'd expect, as I mentioned, that this is not really extremely relevant for Maths Olympiad, as I told right in the beginning, and it is very rare cases that you actually find use for numerical methods. because this is generally done, as I mentioned, in the second year of engineering. So it's definitely not a very what do you say? It's not something that you should be expected to know, though. I mean, since you guys did show this example, that's the only reason why I uh, explain these methods, right? So this is the Newton-Raphson method. The drawback is it requires f dash of x. This drawback should not generally affect you guys, because what you'll be using is generally polynomial equations, where finding the derivative should be easy. I mean, again, for uh, this also means that this method cannot be used by people who do not know calculus, but that's a different story altogether. The reason why this is a drawback is because in computational settings, they might also require people to find, for example, the roots of tan inverse, and the uh, derivative of such a function is not really that trivial, right? So that's the main drawback of Newton-Raphson. That said, there are cases where you might not get an answer, and they're uh, generally these two cases. One is if the initial point is too far away, and the second is if the derivative changes sign. Right, but again, it's so tan inverse of x is given, but for example, what about tan inverse of x square plus 3 sine inverse x? Again, you can probably do this using what do you say? Yeah, you can do it using a chain rule. So there has to be a human generally sitting there, and then whatever sine inverse x into e raised to x or so on. And what if the actual function is not differentiable? So there are a lot of reasons why using this as a standard calculation algorithm might not really apply, right? So as you mentioned, you can human can sit here and apply the chain rule, but it, especially for cases where it includes a lot of different variables, maybe even partial variables, it might not be that simple for a program to for us to automate this. And to be able to find f dash also to the accuracy that you need is another challenge. uh, but yeah, and Wolfram generally works, but again, it's not foolproof, definitely, and this adds a layer of what do you say? So the idea behind all of these methods generally is to find the root as quickly as possible, that is, with as less of compute as possible, and this adds an unnecessarily large amount of compute, right? And again, as I mentioned, if the uh, what do you say, if the value is not differentiable at all points, then that is something that you will have to keep checking that it's still differentiable at the point that you're interested in. In fact, it needs to be differentiable at all the points from x, from your what do you say, from the value you take up to the root, and that's something you'll have to keep checking. But yeah, more importantly, if the initial points are too far away from the root, it might diverge. And let me just give you an example of when that happens. So, for example, what happens in a case like, let's say something like this, and you unfortunately take this point here. Then you take the derivative and finds where it meets the x-axis. Unfortunately, the derivative is extremely small and it will be like really far away from the actual solution, right? And of course, from this you can understand what happens if you actually take a point which is after an extremum, or at any point which is parallel, or at any point where the derivative actually changes sign, because then you'll be completely lost. It diverges extremely quickly. Those are the two known drawbacks that it has. Right, so we have one final method that, sure, we'll do that at the end of the class. One final method to do this that I'll be discussing is a simplification of the Newton-Raphson method, actually, which does away with what do you say, having to compute the value of the derivative. Why? Because we approximate the derivative as f of x minus f of f of xk minus f of xk minus 1 upon xk minus xk minus 1. For those who have taken calculus, this is pretty much what we do to define the derivative, except we know for a fact then that xk and xk minus 1 are extremely close. But we just assume that that is true and use this generalized formula. So then it becomes xk plus 1 is equal to xk minus f of xk into xk minus xk minus 1 upon f of xk minus f of xk minus 1. So mean value theorem does not say that f dash of xk is exactly equal to this. Yeah, it just says that there will be some point whose derivative is equal to this. But either way, so yeah, this then means that we have to keep plugging into one formula itself. But this is more, this is both slower than the Newton-Raphson, and you need to find the keep finding the keep remembering actually the value of f of x. Exactly. So yeah, with that, this class is, I mean, what I had to show was over. We can talk about the 20-sided polygon question if nobody has any doubts. Right. So finally, we have one question that Arjun asked. Yeah. About, so basically the question goes as follows: you have a 20-sided polygon and you need to select three sides out of them such that each side is at least two sides away from the other. That is, if you have selected this side, because this cannot uh, go on to become a 20-sided polygon, but forgive my drawing. But if you have chosen this side, then you cannot choose these two sides. And there are direct ways to calculate this, but one interesting method that Arjun had found was a direct formulation of this into the value 20 over 14 into 14c3, right? So what's happening here? So what the author of this does is that, first, obviously you have 20 sides, so you can choose any one of those 20 sides. You have 20 into something, right? Now, how to calculate this x? Well, you have already uh, fixed the first side, So you can go ahead and throw at least 4 sides. 1, 2, 3, and 4. But the idea that he has is, instead of throwing away 4 sides, let's actually throw away 6 sides, right? And then, yeah, exactly. So the idea that this guy has is, instead of throwing away 4 sides to simplify a 20-sided polygon into a 16-sided polygon, he first throws away 6 sides to make a 14-sided polygon, out of which one side is already chosen. So you have to choose 2 more sides, right? And then uh, just ask Arjun that, please. I'm not really sure. I think it was an RMO question. Yeah. So on the face of it, actually, it's a pretty simple question to do, and I do expect it to be an RMO level solution only, because instead of taking this somewhat unintuitive step that this guy has done, you can just take a single side and then actually count the number of ways that you can proceed. It will be something like, what was it, 13 factorial by 2, or 13 into 12 by 2. So yeah, 13 into 12 by 2. This can actually be counted, and then you say that since you have the first side can be chosen in 20 ways, you multiply this by 20, and it's a pretty simple question that way, and it's definitely. So yeah, Arjun, the other way definitely does take you a lead to the solution much faster. The thing is, you need to be able to think of it that way, and the abstraction that he has done is not something that I'd expect at least an RMO student who doesn't have aspirations of passing the INMO to have. So yeah, let's first go through the other method, and if you are still unable to understand this, we'll come back to this too. Right. So let's look at what happens here. Here, what he's saying is, once you have chosen the first side, then go ahead and delete 6 sides from the other. Right. So then let's go ahead and delete 6 sides from the other to get a 14-sided polygon. Then we can choose any of the other 2 sides. Let's say this was, of course, this is a 6-sided polygon, but I'm just taking an example. Let's say this was the first side, second side, and third side. Then we can go back to what this solution maps to by adding 2 sides between 1 and 2, 1 and 3, and 2 and 3. So this goes back to, let's see, you'll add 6 more sides. Wow. Actually, for the help of my drawing, let's make a simpler question which does not really take away from anything. So you have a 6-sided or an 8-sided polygon. Right. So I'll come back to the solution. The problem is definitely not that difficult. It's just that this single solution is somewhat unconventional. That's all that I'd say. So let's look at a new question just for me to be able to draw. Let's say you have 8 sides, and the restriction is that no 2 sides have to be adjoined to no 2 sides can be adjoined to each other. So if X is taken, then Y cannot be taken. You have to see that this is a pretty direct, or once you solve this, you can apply that directly. What I'm simply doing is reducing the total number of sides. Instead of it being 2 far away, it needs to be 1 far away only now. So what this guy is doing is, he's first choosing the first side, which takes uh 8 number of ways. But once that is done, sure, Asher, once that is done, we know that there has to be one side between each sides that we have selected. So we'll just temporarily delete it and then add it back again. So when we temporarily delete it, we are temporarily deleting three sides. So from an eight-sided polygon, now we have come to a five-sided polygon, out of which one is already selected, right? So this one was already selected. And now we are free to choose any other sides here. Let's say I've chosen this and this. Now, our original question does not allow for this selection because all three are adjacent to each other. But what we do is we go ahead and plug in those three sides that we removed. How? One side between let's call this A, B, C. One side between A and B, one side between B and C, and one side between A and C. And then that brings us to our final solution, which is A here, somewhere here, B here, then one more, whatever, C here, and then all the other, I won't be drawing all the other sides, but all the other sides here, right? And we can see that this is a one-to-one, that any such selections at this point will give you one specific selection here. And how many selections can you have here? You have uh, 5C3 selections. So you can have 5C3 different ways. Except that in this case, we had already selected the first side, when in reality, we have 8 ways to select the first side. So it's not 5, it's 8 that we have. So we have to multiply by a correcting factor of 8 over 5. Right? So yeah, it's uh Arjun, I didn't get your meaning of writing wrong remarks. If your remark is factually wrong and it's relevant, then that obviously negates your proof too. Correct? And that will definitely end up deducting your marks. So yeah, this is exactly the same thing that he has done here. He has gone by 20 over 14 into 14C3, just as it was 8 over 5 into 5C3 here. Uh, oh, you mean not writing an explanation to writing a wrong explanation? I'd say in both cases you'll definitely have deductions, but if it is a wrong explanation, then that should logically have a much higher deduction than the not writing an explanation altogether. The only issue is that, yeah, so whatever you know, like you're sure, it's just best to write that and leave it, because I mean, you can never leave out an explanation thinking that it is wrong, because de facto you're already losing marks. And if you leave out explanations, in fact they might simply say that since you haven't proved this, it's an incomplete solution, and it will definitely lead to point deductions anyway. So yeah, it's always best to write an explanation, and if it goes wrong, then yes, you do end up paying a penalty, but that is that. So in that case, writing a wrong remark that way does put your solution into question, and it should and will increase the uh, what do you say, depth to which somebody will go. Like basically people will go back and read your solution again in a more minute format, and that's something which you have to accept, because giving a wrong generalized statement means that, I mean, generalized formula means that there's a high chance that your specific formula is either wrong or only incidentally correct. So yeah, that way there's a higher chance of getting your what do you say, points deducted. But other than that, so either they have found a reason why the generalization is not as you have said, and then in that case they'll go back and see, find out what assumptions you have made which is not really true, and then that will lead to a negative uh, mark. Or if they do not bother with the whole thing, then it might not affect. So I'd say most probably it will definitely lead to a negative mark. It will definitely not give you extra marks, so I don't know why you would want to write it. Okay, so yeah, that's kind of the end of today's class. If anybody has any doubts, you can ask. So, oh, do you mean this or the original method, the method in the official solution? Oh, so that's simply, so what I'm doing is instead of 20 and two sides, I'm taking it as 8 and one side. Did you understand this solution? Okay, so did anybody else understand this? Is anyone else fine with this? So what we are doing is we are removing three sides first of all, and we are left with a uh, pentagon, right? And the idea is any three sides that you select from here, you can map to three sides here, correct? Or more correctly, given any side A which is already selected, you can then go forth and select any two sides B and C, and then you can map that to one specific side B and one specific side C. Is that correct? Is that fine with you, Arjun? So let's assume that A is pre-selected in both the pentagon and the octagon. Then what we do is we select any two other sides B and C, and then we insert sides between AB, BC, and CA. Insert one side each to create an octagon, and that will give you one solution here. And vice versa, given an A, B, and C, I can remove one side each from these to get a pentagon, to get exactly the same pentagon back actually. So these are two equivalent configurations. I- Is like, are you fine with that? If not, right. The reason we, so what we're doing is, right, because once we have the first side, then my claim is that for any valid configuration here, I can map that to a single configuration back into the pentagon. Why? Because if you have, let's call this X number of sides between A and B, Y number of sides between B and C, and Z number of sides between C and A, right? Then all that I do is I create a pentagon with X minus 1 sides between A and B, Y minus 1 sides between B and C, and yeah, Z minus 1 sides. So given the first side, then it's a one-to-one mapping. There's no multiplication required. Exactly. So since it's a one-to-one mapping, then I don't need to multiply with like 7 by 4 or 6 by 3 or anything. So this was definitely me trying to explain it. You will have to write it like, I'd expect that in such a solution there would be huge chunks of uh, huge paragraphs explaining your thought process, but if you can explain it properly, like basically the idea here is if one side is selected, then you have a bijection here. If you can show that it's a bijection between this pentagon and this octagon, and then finally say that it satisfies this, then yes, you can write that. But as I mentioned, this is honestly, I'd say it's a little too much, especially for an RMO question, and especially when the official answer is extremely easy to understand. No, we cannot write it directly as the AOPS solution. That's definitely not acceptable. There they had just explain like written an outline. So in AOPS, especially in a lot of the comments, you'll see an outline for an answer without a full solution, and that's what it was. um yeah, so this solution again does not preclude you from writing a long solution. In fact, your ability to verbalize this bijection is at the heart of this solution. And if you're unable to prove this well enough, this is a completely, what do you say, written proofs. There's no large mathematical formulas or anything here. So this will be an extremely, generally it will be a difficult to formulate written proof where you're trying to justify this uh, one-to-one solution here. And in fact, the official proof is pretty small here, where what you basically say is that, let's say I have chosen one side here, then I can choose any one of the 13 sides left over. But then let's say I've chosen side X, then then you count the number of sides that you have left to the right of this. That will basically be a decreasing function. So if you choose the first side here, then you'll have like 12. The second side, then you'll have 11 options, and so on. So finally you'll come out with something like this: 13 plus 12 plus 11, and so on. So it's actually, for this solution, it's a pretty direct solution, right? So yeah, if nobody has any doubts, we can end the class. Sure. Uh, Arjun, I do hope that you did understand this well enough. If you do have a doubt still, we can probably catch up over call. Okay, so basically for the next topic, actually, probabilistic NTs is an option. The other option is to leave NT out for now and maybe continue it later and look at graph theory. Again, I might start a poll about the two. Let's see. Um, Let me actually ask, because even I'm not sure what the level of IOQM is. Do you know whether it's more pre-RMO like or RMO like? It will be almost the same as pre-RMO. Okay, so yeah, if you're sure it's almost the same as pre-RMO, I'll check. Okay, so do one thing. Let me just check, and I'm not really sure of it, but I'll definitely ask both Anushka ma'am and let me just find out and I'll get back to it. Both are possible ways, and I'm not really sure they were very what do you say, transparent about it. The thing is, if it's just a higher cutoff, that might not really what do you say, people love, and people generally, if they do only certain sub portions, then they still stand a chance with the older pre-RMO, RMO in more kind of architecture. But if they've simply adjusted the cutoff higher, then somebody, for example, who doesn't like geometry or doesn't like combinatorics or something, might just fail because you know the others were able to do everything, whereas they cannot. So yeah, I'd say the increasing the difficulty is definitely better, but I'm not really sure whether they've come out with any statements saying one or the other, and I'll just find out whether we have any idea about this and get back. Yeah, in the end, it does not matter. Whatever they do, they will like do that. But since this is sound logic, okay. Cutoff depends both on the competition and the toughness of the question paper restaurant. If I give you a pre-RMO type question paper, then with 20 seats, then cutoff will be insanely high, maybe 90% or above. But if I give you an INMO level paper, then the cutoff will be low. So cutoff does depend on the competition, but it also depends very uh, really on the difficulty on the of the question paper. Yeah, definitely depends on both the factors. Okay, then I guess that is the end of this class. I will, yeah, I'll try to, uh, I'll post a form basically like we did right before number theory, uh, to decide whether which subject to tackle next. So everybody, please do uh, reply on that, and then we'll decide what to go to next. So problem solving, if we, I'll have to. So problem solving, especially something which I will take it up with both Anushka, maybe Srijit sir, or we'll decide on what to do for it. Definitely. Okay. Good night, everyone. Have a fun weekend.